Good evening. My name is Angel Barahona-Reyes, and here I am presenting palladium catalyzed acetylation of aryl bromides from the organic synthesis 221-98-6083. Also, for a further disclaimer, I apologize for any noise in the background. I do have family over. So the scale and the optimization of this reaction must be done under a well-controlled laboratory, as it is highly dangerous and costly as well. The most expensive reagent being the acetyl trimethylsilane with the 10.8 milliliters needed. It costs about 326. Furthermore, the check-in process in which this experiment was went through by the checkers. Most of it consisted of them purchasing some of the reagents and chemicals. For example, 6-bromobenzothiophene was purchased from Fluorochem, as well as cesium fluoride. Furthermore, 1,2-dichloroethane was purchased from Acros Organics. And then heptane instead of hexanes, which is interesting because the authors actually use hexanes. However, the checkers chose to go with heptane, and they purchased it from Donaal Chemie. As well, the heptane was distilled after its purchase. And they also purchased silica gel from Barahona-Reyes. As well, ethyl acetate was also purchased from Donaal Chemie and also distilled after by the checkers. So about the reaction apparatus, it consists of a flask, a round bottom flask that is 250 ml with a 24/40 joint. It contains a magnetic stir bar. It also goes through an oil bath. It is flame dried air condenser with a 24/40 joints to match with the round bottom flask, a reflux condenser, and a plug of silica gel, about 50 grams of silica gel, and then a rubber septum with an argon inlet needle with a Persian needle and a plastic syringe that is 18 gauge by 6 needle. So the reason why the rubber septum cannot be seen in this apparatus on the right is because this reaction first goes through a first phase and then the second phase, and I'll get more into depth with that when I explain the procedure. Here are the images of the apparatus, and as you can see on A and B images, you can see the needles, but on C and D, you only see the condenser, but you can't see it fully. So I will show that more later on. And the reagents and starter materials with this reaction are 6-bromobenzothiophene and acetyl trimethylsilane. The reaction was used with cesium fluoride and 1,2-dichloroethane at 75 degrees Celsius, giving you the product of 6-acetylbenzothiophene. So reaction and workup. So the first part of the reaction occurs by equipping a 250 milliliter round bottom flask with a magnetic stir bar and flame drying the apparatus under a vacuum, then cooling it to 23 degrees Celsius under a nitrogen atmosphere. It's very important that it goes under a nitrogen atmosphere, as the original authors used argon. So then furthermore, 6-bromobenzothiophene is added alongside cesium fluoride and tetrakis palladium through the neck of the flask. Then a rubber septum is placed on the neck of the flask and an argon inlet needle in the rubber septum, purging it for 5 minutes. It's important to state that although it's an argon inlet needle, what's actually going through the needle is nitrogen. After 5 minutes, the needle is removed, and then acetyl trimethylsilane is added over 1 minute via a plastic syringe. Then 1,2-dichloroethane is added over 1 minute over a plastic syringe, as seen above. Later on, here's where the needle is removed. So the rubber septum is removed and replaced with a flame-dried air condenser with a 24/40 joint, as seen pictured to your right. And then the reaction is placed in an oil bath that has been preheated for 75 degrees Celsius. This reaction is then stirred vigorously at 800 RPM for 24 hours under a positive nitrogen pressure. And then after the 24 hours has passed, the reaction flask is removed from the oil bath and then it is cooled down to 23 degrees Celsius. Next, the reflux condenser is moved and the mixture is diluted with heptane, about 75 ml. Then the solution is filtered through a plug of silica gel in a 150 ml fritted Buckner funnel into a 1000 ml round bottom flask with ethyl acetate, about 500 ml of ethyl acetate. Once that is done, the concentrate filtrate is filtrated under reduced pressure, about 31 degrees Celsius from 100 millimeters Hg to 50 millimeters Hg. Then the purified brown solid, the brown solid is purified via a column chromatography using an OD 7.5 by 12 centimeter column of 250 grams of silica gel. Then the fractions are collected using a 25 milliliter test tube as pictured to your right. It creates this yellow, kind of off-white solid substance. So the purification. The purification occurs using a TLC analysis on silica gel with 9:1 ratio of hexanes to ETOAC. It is visualized with UV irradiation at 254 nm and P-N-acetaldehyde. So the starting material, RF value is 0.73 with no color, and then you can see an active UV. However, the desired ketone product's RF value is 0.32 with a pink color, and also the UV is active. On the right, you can see the image of the TLC collected by the authors, and it shows the starting material, the co-spot of the starting material and reaction mixture, as well as the reaction mixture. You can see that they're both closely, however, not the same numbers were given. So then the characterization and proof of purity. So the authors determined a purity of the product of 6-acetylbenzothiophene by using 1,3,5-trimethoxybenzene as the external standard. They also performed 3 reactions at a half scale that produced the products between the yields of 65 and 73, which is not too low nor too high. Then a second run at full scale was also conducted, and it provided 4.51 grams with a 68% yield. And then at last, a half scale reaction using the following molecule PD PPH34 provided a 76% yield, which is really high, however, only produced 2.51 grams. Safety note and hazard warning. The dangers of the chemicals and reagents used in this experiment vary. We have a couple of asphyxiants, neurotoxins, and dangerous inorganic particles. Some of the asphyxiants are like acetylenes, nitrogen, methane, and argon. For example, acetylene is also very explosive, and inhaling some of these chemicals can actually cause nausea, and a bunch of other side effects that are deadly or very harmful and sometimes irreversible to humans, as well as neurotoxins like hexanes can cause reversible or sometimes, if and when it's able to be saved, damages to the human body. As well, dangerous inorganic particles like silica gel, once inhaled, can cause the particles to go inside the lung and be retained for years, which is pretty bad for humans. So for the discussion section, it is possible to perform this in our lab, absolutely, only with the following precautions of using the fume hood correctly and wearing and using the right equipment as pictured on the right. Goggles is super important. Using the fume hood is very important in order to protect yourself from inhaling any of those inorganic molecules, toxins, or as well as any of those asphyxiants or neurotoxins that can cause your life, as well also wearing a lab coat, not wearing long jewelry, not having your hair, if you have long hair, not having your hair tied. That would be very important if you have long hair. But in essence, I strongly believe that it is able to perform this in our lab, since we have used a condenser and a reflux condenser as well, and a bottom flask, and a bunch of the equipment used in this experiment we have had used in our laboratory. And this information about the authors. There are a couple authors who have bachelor's in chemistry, like Milana Mehta, and then Andrew Culligan, who has a bachelor's of science in chemical biomolecular engineering, and also Neil Garg, who's a professor at chemistry, and Kenneth and Trueblood Endowed Chair at the University of California, Dresser. Martina Drescher is also the lead technician of the MOLY group at the University of Vienna. Daniel Kaiser contains a PhD, as well as Zakariki and Yuku Malkawa. Thank you, and that is all for today.